So I lied. I said I wouldn't say anything about history. So on the first slot, I say that the cyclotomic trace was invented by Bøgstad, Chang, and Madsen in the late 80s in order to prove the Novikov conjecture. And, well, of course, if I gave a history talk, I'd have to talk about the Dennis trace map already in the early 70s. But what I'd really also want to mention then would be a beautiful paper by Bloch, where he talks about what he calls the tangent space of algebraic K-theory. So what does he do? He takes algebraic K-theory of a ring A, he adds a square zero ideal, so he essentially is talking about the ring of dual numbers. Well, from the K-theory of the dual numbers, he subtracts the K-theory, and he considers what he gets. And he gets the Kähler differentials, you notice. He uses K1 and K2 calculations from way back, and he sees that the Kähler differentials sit there. So he's really seeing cyclic homology popping up way before anyone else did. And for this audience here, who is all Hermitian, you may enjoy that he wanted 2 to be invertible for doing what he did. Already in 72, Bloch saw that 2 should be invertible sometimes. Well, but the trace methods are not only good for proving the Novikov conjecture, luckily, they're also good for calculations. There's an entire slew of calculations that are due to trace methods. You could say that there are 2 methods for calculating K-theory. Either you're having motivic homology or you're having trace methods. And sometimes you do both. But even if you can't calculate, the trace methods are often very useful for detecting structure of algebraic K-theory. So even though we're going to see that the difference between K-theory and topological cyclic homology in some cases is not very big, even when the difference is very big, what survives to TC may be a very important piece of what K-theory actually is. I want some perspectives on what I'm going to do. This one actually is sort of a personal thing, because way back in the early 90s, when we first thought that we should be able to prove that K-theory and TC were very closely connected, Randy McCarthy had this vision that the TC should somehow be the polynomial approximations, well, the limit, the power series approximation of algebraic K-theory. And he wrote out on the blackboard some sort of proof of it. And then he found another proof, so nobody knew about that proof any longer until in 2012, it all of a sudden reappeared again. And what is nice is that this is some sort of Witt vector construction. And it's not the Witt vectors that we heard about this morning, but some other sort of Witt vectors. We'll come back to that. And again, it takes, well, let's get back to that. The easiest way of seeing the cyclotomic trace is that it is the inclusion of fixed points into some enormous gadget that turns out to be topological cyclic homology. That is definitely not useful for calculations, but it is useful to see that it's a very nicely behaved map. So it's an easy way to define it. And lastly, Waldhausen had, when he defined algebraic K-theory, you could say that one of his guiding principles was that while K0 is the universal abelian group that splits short exact sequences, K-theory should be the universal functor to spectra that splits short exact sequences. And of course, well, that was a very nice guiding principle for his S-dot construction, and now it's can actually be framed within the language of infinity categories, and as such, then the universality properties for K-theory demands that the trace, as it is, exists by work of Bloomberg, Gipner, and Tabuada. Okay, so let me bore you 5 seconds about how great K-theory is. So it's good for number theory, and that's where it starts in the late 1900s with Kummer, when is a number ring a unique factorization domain? When is there an easy proof for Fermat's last theorem? Obviously, this is not a chronological list here, but stable homotopy theory has been very important for us now. Well, there's many things you could say here, but one of the things is that important ring spectra that we want to know about actually come as algebraic K-theory of things, so we can control them very, very nicely. That's perhaps going the other way around. And the real start for algebraic K-theory was Grothendieck, and so we're talking about algebraic geometry, and very shortly afterwards, Etienne Hirsauch, topological K-theory. Relevant to Hermitian K-theory is Waldhausen's vision for algebraic K-theory of spaces, and algebraic K-theory of spaces has to do with diffeomorphisms of manifolds, of high-dimensional manifolds, and here involutions become essential. C-star algebras, analysis. Let's do some examples. The sphere spectrum itself is the K-theory of the category of finite sets. So finite sets and disjoint union is a thing that you can take the K-theory of, and out comes the sphere spectrum. I said this was going to be embarrassing. If A is a ring, then what K-theory of A is, and here I introduce some notation, so it's good for something, K-theory of the category of projective, finitely generated projective A modules. And, of course, short exact sequences of projective modules split, but they do not split functorially. So K-theory has something to say. And likewise, Etienne Hirsauch, when they talk about complex K-theory, they're talking about the K-theory of the category of complex vector bundles on the space X. Okay. I don't care what machine you use. Use any machine you like. We saw this morning symmetric monoidal categories, and it's this nice vision of Thomason that connective spectra, well, that has a nice, the homotopy category of connective spectra is the same as the homotopy category of symmetric monoidal categories. So if you want to think about connective spectra, or if you want to think about symmetric monoidal categories, that's your choice. We saw it as the group completion. That will not be that important for us right now, but it is in the sense of connective spectra versus symmetric monoidal categories. Of course, when we saw that the sphere spectrum was the K-theory of finite sets, what you do is that you add negative finite sets, and you get the sphere spectrum. And lastly, you can view it as the universal functorial splitter of exact sequences. Okay, so what properties does it have? And some of these are going to be important later on. First and foremost, in regular situation, it is A1 homotopy invariant, in the sense that for a regular ring, K-theory doesn't care whether you're talking about the K-theory of the ring or its polynomial rings or anything like that. Being defined as a functor on the modules, it's of course Morita invariant. It only depends on the projective modules. And it satisfies various forms of descent, tau being the spooky one, where it's actually Lichtenbaum-Quillen conjecture in certain cases. But then things aren't so nice anymore. So when I say that K-theory is troublesome in the presence of singularities, that doesn't mean that I say that K-theory is wrong when it gets to singularities. You'll never hear me say that K-theory is wrong. K-theory is always right. So it's K-theory, if you have the affine line and you have the affine line and you glue them together in a point, K-theory will tell you, no, you don't have my arbitrary sequence for that situation. And I'm sorry to say that's just a fact of life. So, but that makes it very hard a priori to calculate when you have slightly singular situations. Smooth things, of course, are awfully hard, but at least there you have some structure to work with. And also, it's sensitive to deformations. So if you have a field and you just give it tangential information, you say take a square zero extension of it, the K-theory it just does something else. So it's highly complicated to see how K-theory behaves when you have singularities and when you have slight deformations. But that's what we're going to fix in the course of this lecture. So we have the three good things, and we keep them, and we have the two bad things, and we fix them. Questions? Okay, I said that I didn't care about the machine, but there's one thing I want to keep so that I can talk about the setup the way I want to. I want to insist that the K-theory comes as some spectrum, K of C, and it's actually the objects of something that is called K of C again. So say that K of C is a symmetric spectrum. So that is, a symmetric spectrum is a simplicial functor from some category to spaces. Well, this is a functor from the same category that governs the behavior of symmetric spectra, except that it doesn't land in spaces, it lands in simplicial categories. So I want to insist on that. So just remember, this K-theory here is the usual K-theory. It's a spectrum, and this thing here is a spectrum in categories. Or sorry, before I take the objects, this thing here is a spectrum in categories. So I'll try to remind you of that when we get that far. Yes? Yeah, so in even more primitive language, it's instead of going all the way to spaces, so a spectrum is connected with lots of spaces. Here you have a lot of categories in the space in lieu of those spaces. Okay, so let's go back to Bloch. We deform our ring that we start with here. A is just a usual, ordinary, discrete ring, and I take a square zero extension of it. So P here is an A bimodule, and the multiplication in A plus P is so that, well, it's the usual multiplication in A, and if I want to multiply something in A with something in P, I use the bimodule structure. And if I have two things in P that want to multiply together, this is 0. So that is the square zero extension. Okay, so luckily that is very easy to understand the isomorphisms of such a square zero extension. So if you can see this far up, yeah. So if I take GLN of A plus B, they taught me this awesome trick that I cannot hide. Yeah. What is that? Well, you have an n by n invertible matrix of A plus P, well, it can be an invertible matrix in A, but it can also be, well, 1 plus any old matrix in P. And so here, of course, you have that if I have 1 plus m times 1 plus n, that is equal to 1 plus m plus n, and then I want to multiply m and n, and I get nothing. So you see that the multiplication here is just addition. So it's just addition here in this factor here. And together with fun facts about the S dot construction, this boils down to the following equation. So if you take K-theory of A and you add this tiny p, which is so small that its square is 0, and then you divide out by K-theory of A, that you subtract K of A, what you get? You get a wedge over the objects in this category. And here you see P again. So this is really, these are really, if you think of this as keeping a placeholder of the rank of the matrices, the n here is kept track of here, and the P is over there. And the bar over there, don't worry about the bar. The bar just comes from the fact that when you calculate algebraic K-theory, then you take the nerve of a category. So the nerve of the category is then hidden here as the bar of this additive thing over there. So if you so P was very small, but if you let it really go to 0, that is to say you let the connectivity grow, you take as many bars as you please for P, and then you loop down one more time than you think, then you get the differential of K-theory at A in the direction of P, so to say. So I flashed this for you now because I want you to recognize it a wee bit later. Yes? Yeah, okay, so K of A was this category. It's a functor from some indexing category saying that it really was a spectrum, and each of the values then are categories. So this is just ends in each of these categories. That is a spectrum. So these are objects of these things here. So when the K is upright, I've taken the objects. When the K is slanted, I have not. This will be hard to keep track of, and I'll try to remind you. So this is then the endomorphism in this category. It's just the matrices, so to say, where I've split the short exact sequences. Okay, because I want to talk about the homology of categories. If I have a category C and a bimodule is just a functor in two variables, one contravariant and one covariant. This is a category, so it has to land in sets. I call it still a bimodule. Then the homology is a simplicial fellow, and it is the following simplicial fellow. You take the disjoint union, the coproduct, over Q plus 1 objects in C. And then you have, what is this? This is a string of morphisms starting in CQ to CQ minus 1 to CQ minus 2 to C1 to C0. So this looks like the nerve. This looks very much like the nerve. And then at the end, I have this bimodule where I close the loop by going from C0 to CQ. And if the bimodule is the constant functor that sends everything to a point, this is the nerve. Then it's just the elements in degree Q are just strings of morphisms from all the way from CQ down to C0. And if my module bimodule does not depend on C naught. So PCQ is the same as M of C naught CQ. Then this is exactly Bousfield and Kahn's formula for the homotopy co-limit of P. So this is familiar turf. And if your category by chance has the following nice property, that its morphisms are not just sets, they're actually abelian groups, and composition is bilinear, so it's an ab category in that language. Then what you do is that you, of course, replace set by abelian groups, so this is then a bimodule in the usual sense, times with times with tensor, times with tensor, and this disjoint union then becomes a huge sum. And that's Hochschel homology. Why is it Hochschel homology? Well, consider the case where your category C has just one object. Well, call it star that object. Then the endomorphism of that single object is an abelian group, because the morphism spaces were supposed to be abelian groups, and composition then gives that a ring structure. And your bimodule, as applied to the only object, then becomes a bimodule P over your ring, which I now call A. And the Hochschel homology of this one-point category then exactly is the usual formula for Hochschel homology, namely as in degree Q, P times tensor, P tensor A tensor itself Q times. So if A is some sort of flat something ring, then that is Hochschel homology by anyone's definition. And lastly, if C is a spectrally enriched category, then of course, and spectrum here can be in any symmetric monoidal category of spectra, then replace sets by spectra times by smash and coproduct by pointed coproduct. And then we have THH. And again, if your category has just one object, then that is exactly the same as THH of the ring spectrum I get by applying my category to the only object, the endomorphisms. Composition here gives a multiplication of that spectrum. Questions at this stage? So, okay. So this is THH. And probably I should say lots of flatness hypothesis and whatnot on everything, so that smashes are nice. Alternatively, you could use Buckstedt's formulation, where you suspend, where you loop everything down after you have taken this at certain spheres. But I want you to compare it with the tangent space of algebraic K-theory. So K of A plus P divided by K of A. That is the wedge over some category, admittedly a spectrum of categories, and then some module here, bimodule here. So, of course, there's not a string of things as we have here. So this looks like the zero simplices of something. And yes, of course it is. It is the zero simplices of THH, of this spectrum of categories with coefficient. I've just written P, but of course I mean this module here. Okay, so I guess I lie now. So why I should speak truly. So only correct statements, please. Okay, so this thing here. So here, this thing was supposed to be a spectrum. This thing here is, well, just an abelian group. And so what you would like to take is just to take the Eilenberg-MacLane spectrum associated with this simplicial abelian group. And we've started a wee bit by taking the bar. And so what you should do is that you should take the bar lots of times in order to get a spectrum. But that was exactly the procedure you did in order to take the differential of K-theory. You were supposed to take the bar of P lots of times, and then you were supposed to loop back. So forget about the looping back. We're okay with staying in spectra here. So you see that the tangent space of K-theory, well, at least when I let the connectivity of P grow beyond everything, that is exactly the same as the zero simplices of topological Hausdorff homology. So the zero simplices, it doesn't matter. It turns out that the zero simplices or the entire thing, those are equivalent when the input is K-theory. Okay. So the differential of K-theory is this thing here. But that's the best linear approximation. And you would have assumed that the best linear approximation would be something simpler than what you've started with. But now we've just put K-theory inside THH. And that seems bad, but it's not. Because under reasonable situation, THH just swallows the K-theory. It just takes away the K-theory. So THH of this K-theory thing is just THH of the category itself. So that has to do with THH being nice on products and whatnot. And also, it is exceedingly Morita invariant. THH of the category of projective A modules is the same as the category with just one object, namely A itself. So even though the differential seemed like an enormously complicated thing, it is just an enormously complicated thing, but less enormously complicated than it was before. So now it's just THH of something. But of course, the differential is just an approximation. So the question now is, how can I reconstruct K-theory of A from this rather, supposedly simpler thing? And there is one answer to that that is slightly cheating. And that's the following. So we are interested in the case where the bi-module is actually C itself. Then THH looks like this. And there's a cyclic action here. I can just permute or rotate around here. And when you have a cyclic object, then you can, of course, realize, and it gets an S1 action on it, and it's very easy to calculate the S1 fixed points. Let's do that here. So if X is a cyclic set, and you realize that, and you take the S1 fixed points, then that's exactly the vertices of X that have the property that if I take the degeneracy of it, well, then I get the same as if I take the degeneracy and then use the cyclic permutation. So in our situation, we started with an endomorphism F. S naught of F shifts that up one, so then I should have two morphisms. I have F, and then I have the identity. This degeneracy just inserts identities. Whereas the cyclic permutation is, in the other order. So if these two things are the same, that implies that F is equal to the identity of C. So the only thing the actual fixed points remember is the object C. So the actual fixed points are just the objects. That is to say, the S1 fixed points of the first differential of K-theory is nothing but K-theory itself. So it sits inside there as the fixed points. That is nice. But the problem is, of course, that taking fixed points, then I'm definitely stuck with algebraic K-theory sitting inside there. I cannot use the homotopy equivalence between THH of the K-theory and THH of A. Because, well, naturally, the fixed points of THH of K-theory is K-theory, while the fixed points of THH of A, well, that's the objects of A, that's just a point. So I have to do something smarter, and that's, of course, exactly what Buxton, Chung, and Mattson did. There were some precursors to this. Rationally, one knew that the homotopy fixed points were quite good approximations. So actually, the trace from K-theory to the homotopy fixed points, at least under rationality assumptions, was just as good as topological cyclic homology turned out to be. But if we're not taking if we're not going rational, we need more refined tools. And very good. And here's what you do. This is one way of saying it. There are many ways of saying this, and some other ways have some advantages over the way I do it now. So you saw we were going to take lots of smash powers of the ring A with itself. So for convenience now for this presentation, I assume that A is a commutative ring spectrum. And let's see, so either I say derived or I'm honest, and I say that X here is a free G set where G is a finite group and A is sufficiently cofibrant. And then I take the G fixed points of A smashed with itself X times. Okay, so what I really want to do is to let X be the circle, and I want to take G to be the circle, but let's not be that ambitious, because that's not that smart. Well, if under these circumstances, I have a restriction map going down from the fixed points to the orbits in the category of commutative orthogonal ring spectra, which may seem scary, but it turns out just to be the smash product of A with itself, not the number of times there are elements in X, but the number of times there are orbits of X. So Buxton, Chung, and Mattson saw this as a restriction map from, well, they looked at G equivariant maps, and then they restricted them to maps of fixed points, but we can look at it this way here instead. So here is a fully easily understandable map, and if A weren't a ring spectrum, if A were a set instead, a pointed set, then you would have seen this immediately. Because what is, if I take the X-fold smash product of a pointed set with itself, and I take the G fixed points of that, what does that mean? Well, that means that, well, this X-fold smash, that's a string of elements in A, and if I take the G-fold fixed points, that means that that string has to repeat itself every so often. So I can just chunk off one piece of that, and I have exactly this thing here. So in that case, this would be an isomorphism. And on cofibrant objects, we're not that far from being in sets or spaces, so the remnant is this map here. But, okay, so that's nice, but the really nice thing is that the homotopy fiber, we understand it fully homotopically. So these are the categorical fixed points. They are very badly behaved a priori. This is very well behaved, and the homotopy fibers is also nicely behaved. I'll give you an example in a moment where you see how useful this is. But some of you may be way more familiar with saying it this way. We may identify these orbits with the so-called geometric fixed points, and then this restriction map turns out to be exactly isotropy separation. Okay. So here's an example. From the fixed points finite group to the orbits. And now I've moved away from X being a finite set and I allow it actually to be any simplicial set. That is perfectly fine. Just need to be a wee bit careful and that works. So here I've taken the simplicial set S1 that is big enough so that CP acts freely on it. And that's a model for THH of A, CP fixed points. And then I take the restriction map and I go down to the smash powers of S1 mod CP. But S1 mod CP is the same as S1. You just wrap it up and you get THH of A. And the homotopy fiber is very easily, neatly given. The homotopy orbits of that. Okay, so the fixed points fiber sequence where at the bottom, at the base spectrum, you have THH of A, and the fiber is the homotopy orbits, which means that if you know that homotopy orbits are homotopy invariants, so by induction, you will know that fixed points under finite subgroups of S1 are homotopically fully controllable. So you may want to approximate taking the entire S1 fixed points, not by the entire S1, but by an enormous finite subgroup. And sort of we know that these lie densely inside there, so oughtn't there to be some hope there? The question that Böse-Chang and Madsen had to address was, how do I access these enormous subgroups? How do I let the subgroups grow? And there are two answers to that, and their answer is do both answers simultaneously. They define topological cyclic homology, well, I fix a prime here, as the homotopy inverse limit of the fixed points of the cyclic groups of prime power order by means both of these restriction maps and of the natural inclusion of fixed points that you may have. Well, that you do have. And if you just mix in the homotopy fixed points of all of S1, you get an integral version and you get an integral cyclotomic trace map that is exactly the inclusion of fixed points. So that is the construction of the trace map. Okay, so just a word on, yeah? Yeah, okay, so we knew, okay, so thanks. We knew that inside here, inside topological Hochschild homology, and now allow me to write K-theory of A instead of A there, because we know that everything here inside is homotopy invariant. So instead of writing A, I write K-theory of A there. And then K-theory of A sits as the S1 fixed point of all of this. And it really respects all this structure. Just sits in there. And then, of course, so the honesty here at the bottom here, that's a zigzag, is just taking the K-theory out of that in order to land exactly here. Thanks for the question. It was very relevant. Yeah, so that, okay. So this thing here is, so I have a model for THH where this thing here is the actual fixed points, S1 fixed points. I take this construction here, which is homotopy invariant, and I've written it out for A here, but I could have written it out for K of A instead. If I wrote it for K of A instead, then you'd see that this sits exactly inside here. And then I take the K-theory out again because this is homotopy invariant, and that is the zigzag down there. Did I answer the question? Okay. Let me get back to the tangent space of K-theory last time here. And there's just a wee bit here. I've taken away a bar construction. So this is not this is not the tangent space of algebraic K-theory anymore. This is not Ka plus P minus K of A. This is something else that looks more like the endomorphisms, K-theory of the endomorphisms with coefficients in a bimodule. But this is a legitimate functor in P as a bimodule of A. And if you take the Taylor power of that functor, polynomial approximations, then each stage here are really reminiscent of the restriction maps that we had a moment ago. And the differentials that usually are homotopy orbits over the symmetric groups turn out to be homotopy orbits over cyclic groups instead. The rest is a free part that vanishes. This looks very, very much like the restriction map. And each of these look very, very much like some sort of Witt vector with coefficient construction. This is due to McCarthy early on, and Ayelet Lindenstrauss, and he wrote a paper together in 2012 building on those ideas, and probably adding a lot of new ones. This goes way back in history. This goes back to an old paper by Almquist, I think it's in 71, where he studies exactly this K-theory of endomorphism. He studies K0, that is to say. And he finds that K0 of the category of endomorphisms, so then P is equal to A. So the category of endomorphisms, that is a dense subring of the Witt vectors. It is dense subring. So the Witt vectors here, now we're talking about the big Witt vectors. Height. So you have the big Witt vectors, which is the power series that start with 1 under multiplication and some interesting multiplication on that again. Inside there, you have the K-theory of the endomorphisms of A, and I divide out by the K-theory of A. And it turns out that this subring is dense, and it's exactly those that can be written as fractions of polynomials inside here. Well, again, K-theory is the extension of K0 just to spectra, and the statement that we just saw was some sort of extension of Almquist's observation to the category of spectra. And this has also been expanded on by several other authors in very interesting papers. So it's a version of what you get if you take the topological Hochschel homology with fixed points in cyclic groups and you let the restriction map run.
Sorry, I always thought KAP is the category of morphisms from C to C tensor P.
Yes, that is the same. But then I would have to change this thing here, so I didn't. But it's the same as what you were thinking. So so the problem is that I haven't claimed that this is a projective A module. If I did, I could have said the same as you did. Other questions?
Is there a map from one tower to the other? Is the tower with the TRs?
Mm-hmm. I think, let's see, so it doesn't match exactly up, but it's very, very similar. Okay, so now that we have defined the map, we should ask ourselves, what is it good for? Both K-theory and TC satisfy what you might call one-connected descent. So it doesn't. So you're pretty free to change your ring spectrum as long as you don't mess up your pi naught too badly. And what we're going to see is that the difference is locally constant. So if you know K-theory of A at one point, here is K-theory, then, and here is TC, and here is the difference between them, well, that difference close by is not going to change at all. So if you know K-theory of A here, you know TC of A here, and you know TC of B there, then, TC of B there, then you know pretty much K-theory of B here. So it's very, 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 very good to be able to calculate topological cyclic homology. But K-theory has some exceedingly irritating features. There were 0.4 and 5 on my list. It's not rigid, so if I just extend it by a small deformation, then strange things happen. And it's not, doesn't satisfy closed excision. So if I glue two things together like this, bad things happen. But then the strange thing is that those bad properties are not only shared by topological cyclic homology. The correction term that you need to add in order to have a statement, they are the same for K-theory and TC. So, well, here we saw the example of locally the same. That's K-theory doesn't stay locally constant, but its behavior is the same as that for TC, and the same is true in these excision situations. So in that sense, we only need to calculate the TC side. That is not to say that calculating TC isn't enormously difficult, and it's enormous respect for everybody who are able to calculate topological cyclic homology. Let's be a wee bit more precise. So here is the statement about, nilpotent kernels. So if I have a map from A to B, connected ring spectra, I have to be honest, I'm very, very bad at tackling ring spectra that are not connected. I'll have a wee bit to say about it, but not much. But most of the time, I have to stay in the safe haven of connected ring spectra. And if that map on pi naught is a surjection with nilpotent kernel, then this diagram here is Cartesian. That is to say, the homotopy fibers are the same. That was essentially the statement down there on the blackboard. So examples where this has been important, you can go between, say, the integers. So all of these, what do all of these rings have in common? They have in common that pi naught is the integers. So you take the sphere spectrum on the loops of a simply connected manifolds. You take the sphere spectrum, you take mu, you take ku, complex Bordism or K-theory, and they have all pi naught hz. So the K-theory of, I can, for instance, put hz down here, and any of the other buggers up here. So if you're able to calculate K-theory of z, please do. I think that is some sort of almost confirmed conjecture. And TC of z, we'll come back to that. Then it's just left calculating K-theory of A, and I should add the maps here. The maps here are often highly mysterious. The second thing is due to Geisler and Hesselholt in 2011, building on work of Cortinias, who did the rational case. So assume that you have two maps, A1 and A2 to A, that are surjective on pi naught. Then you can wonder, and this here is the example of kx times ky over k, that's just the cross. And you can wonder what happens if I glue A1 and A2 along A. So that is the same in the affine world as the product of A1 and A2 over A. So this is typically one of these singularities. Well, I promised you that the deficiency of K-theory is the same as that of TC, and here is a precise statement of that. This cube here is homotopic Cartesian. That is to say that the iterated fiber of this square is the same as the iterated fiber of that square. So not only do we have control of what happens when we have open embeddings, we also have some sort of control for closed embeddings, at least if you're able to calculate TC. And of course, one of the people in the audience is awesome about doing those kind of calculations. So for the case where K is some sort of nice field not too different from FP, then Lars Hesselholt calculated K-theory then of K of xy mod x times y, the cross. And what is, of course, funny here is that whereas K-theory often is A1 A1 invariant was the word I was looking for. Oh, okay, good that at least you are awake. So, for instance, if K is regular here, these two things are the same. This is usually far from being the case for TC, so you have to calculate these fellows here as well as that fellow there before you're done. But this situation, equivalences, so really we're calculating the difference between the K-theory of the field then and the cross up there. Okay, so those are the two rectifications of the two deficiencies I had for algebraic K-theory. We had control of the case when F was a surjection with nilpotent kernel. That's exactly at the boundary of convergence, by the way. It's from this Taylor tower considerations, it is clear that if pi naught of f were an isomorphism, then everything should be fine. But it actually goes well when we have nilpotent kernel as well. So these small deformations and this closed excision situation. So I hope I have guided you to an extreme desire to calculate topological cyclic homology. Everybody now wants to calculate topological cyclic homology. And then, of course, my task now is to make you not do the calculations that have already been done. So I'll tell you about those calculations that have already been done, and you do the rest. Okay, the start of the induction is the prime field FP. And Quillen notices that the K-theory of any ring of characteristic P, well, if you look in after P completion, that is a rather simple thing. All the higher homotopic groups vanish. I guess I should ask that it's perfect as well. And FP is as perfect as you want it to be. So you have a perfect ring of characteristic P, then all the higher K-theories vanish, and you're just left with K naught, and that is just HZP. So that's good. And Hesselholt and Maassen calculate K-theory and a TC of FP, and lo and behold, they get this conclusion here. So after P completion, they get a copy of HZP in degree 0, and annoyingly enough, they get a copy of HZP in degree -1. Sorry about that. But it isn't that strange, actually. So in here, there's a Witt vector construction sitting, and this is the kernel of the 1 minus the Frobenius, which turns out to be the identity. So it's just HCP, and here is the co-kernel sitting in 1 degree lower. But from there on, it really takes a life of its own. So now we know it. So as I said, now we know it for one. We know the answer for both of TC of K-theory for one ring. So all rings that are fairly close to FP are now in our reach. I'll have something more to say about this. This is definitely not trivial, and it's a beautiful paper by Hesselholt and Maassen that ends up with the following statement. So you have a connective ring spectrum where pi naught of A is a finitely generated algebra over the vectors over a perfect field of characteristic P. So your connective spectrum, the demand is that pi naught of A should be a finitely generated algebra over the bit vector over a perfect field of characteristic 0. Then we have a fiber sequence like this. And so this term here looks scary, but it's, of course, the non-scary part. It's one suspension of an Eilenberg-MacLane spectrum of a single abelian group, the co-kernel of 1 minus f, the Frobenius endomorphism on the bit vectors on pi naught of A. So that is just one single group sitting in degree -1. And that is the difference between K-theory completed at P and TC completed at P. So for these rings, and we have lots of them, then calculated K-theory completed at P is the same thing as calculating TC completed at P. So that is essentially moving from this single ring, and you get all of these connective ring spectra for free. Okay, perhaps I should say something about, so there are some non-trivial things that, well, there are many non-trivial things, but in particular, it's not just, the local question is not as local as you'd think, because you're actually moving from FP to the bit vectors. And that means that we somehow need to be able to handle infinite or inverse limits of rings. And in certain cases, K-theory and topological cyclic homology do have what you could call continuity properties. That is to say that, well, ZP is just the bit vectors of FP, the inverse limit of Z mod P to the n. So here the limit is on the inside, and here the limit's on the outside. And I think it's the theorem of Panin that says that after P completion, these two things are the same. And there are similar theorems in similar situations. So we get to K-theory of the p-adic integers through knowing TC of the p-adic integers, but never does anyone require any knowledge about K-theory of Z mod P to the n or TC of Z mod P to the n. And that's actually surprisingly hard. At the present, of course, we have just partial knowledge about either of these two things. So I guess, okay, so TC has a quite good continuity property. I should end at this slide, by the way, as in the sense that TC of the inverse limit of an iadically complete finite Noetherian ZP algebra, well, then the limit just passes on the outside. And Geisler and Hesselholt used that kind of result at certain stages in order to deduce continuity for K-theory itself from continuity of TC. And, well, I've talked about K-theory completed at P. If I complete at a prime different from P, that is totally different, because then K-theory actually is rigid. So, for instance, K-theory of the p-adic integers is equivalent after L-adic completion to the base ring FP. Okay, I think I should stop there. I've gone for 1 hour. say that